So, I'm going to give two lectures on lower bounds and quantum complexity. It's a field that has been very active for almost 20 years now, and I will try to show you some of the main results. I have to select some, I couldn't show everything, obviously. And as we will see, it's also a field where we're working at a very low level of quantum computing, which means that on the one hand, the proofs are quite accessible because it eventually reduces to combinatorics and linear algebra, but it's also a field that tends to be a bit technical. So I selected a few proofs to show you how these things work, but I will, for the proofs, I won't go in full detail. I will try to give you the main intuitions. Alright, so before talking about quantum Fourier complexity, let me tell you about the classical model that was introduced before. And the classical object that corresponds here is a decision tree. So it's a very simple situation in which we're given an input x, and we are asked a question about x. And eventually in this talk, it will mainly be a Boolean question about x. So the answer is 0 or 1. And the way you access to x, in general, you have your input that is written in front of you somehow, and you read x through queries. So you can ask for an index I. You can ask for the value of x on this index I, right? So the ith bit of x. All right. So if you think about it for a minute, this is called decision tree because you can represent it. You can represent this as a tree. So the way it's evaluated is the following. You start at the root here, and the root is indexed by one of the indices, this one here. By the way, I just drew this is just a random function, I'm not even sure it's consistent, but, or a random tree. So you ask for the first bit here, and if you get answer 0, you continue on the left here, and otherwise you go to the right. Right, and you do this then for input, for the second bit here, third bit, fourth bit, and when you reach a leaf, this is supposed to give you the value of the function. And the height of this tree there, if you can write down the best possible tree, the smallest possible tree, the height here gives you the classical Fourier complexity of the function f. Right, the function f is the one that is computed by the leaves here. All right, so here is a decision tree, for example, for a specific function. This is the OR function on 4 bits. So I first ask for the first bit. If it's a 0, I continue. If it's a 1, then I know that the OR of the 4 bits is 1, so I can just add the 1. And otherwise, I continue. And eventually, if all the answers I got were 0, then I add 0. Right, so this is the OR function. This is a function that we're going to look in many situations here. Because if you think about it, some of the functions that Stacy mentioned the other day, they are very well represented in this model of quantum Fourier complexity. So the OR function, it corresponds exactly to the unstructured search problem that was solved by Papert, for which Papert has given a quantum algorithm, because this is exactly, you have this list of positions and you want to know if one of them evaluates to 1. And we know from Papert's algorithm that this, you can solve this problem with square queries. Another interesting problem, and important in this model, is the element distinctness problem, in which you have a list of numbers, and with the promise that either they are all different, or there is exactly one pair with the same value. Right? And the goal is to distinguish between these two situations. Right, and by this, has introduced an algorithm. So Stacy showed you the other day an algorithm making n to the 4/3 queries, I think. And you can also do it with there exists an algorithm that makes n to the 2/3 queries. And one of the very nice things about this model is that it's possible to prove lower bounds. So just to make you think what is a lower bound, I have this graph here. So the blue curve in the middle is the complexity of f, which means the minimum number of queries that are required to solve solve f on worst case over all possibility with x. Right, and the green curve on top is an upper bound. So this is this big O notation here. this big O notation here. So an upper bound, usually you find it through an algorithm. You give an algorithm that solves the problem. It might be non-trivial, but this is how you prove an upper bound. And the yellow curve in the bottom is the lower bound for the query complexity, which means, I mean, it's basically any function that you can use to lower the real complexity of the function. And it's something that doesn't happen very often, but in this model of query complexity, we have very good methods to prove lower bounds. It's not true in many models, Turing machines, even circuit complexity. It's very hard in general. Proving lower bounds, it's a very hard problem because you have to show that no matter what algorithm you use, you need to make at least, I mean, you need to spend at least that amount of energy or that amount of work. And in this case, the work is the number of queries. But still, as we will see, for query complexity, we have a very long history of lower bounds. And in fact, this history even started very early with a paper of 1997 where Bennett and co-authors, they proved the lower bound for the OR function. And the chronology here is a bit misleading. This is the year of publication, but this lower bound was known before even the Kroger's algorithm. So, I mean, they had this lower bound, it just took them longer to publish it. And it's a very interesting lower bound. It uses a very ad hoc argument. But what I want to focus on in the two lectures are lower bound methods. So it's a general, so what I will show you are two general methods given a function to prove a lower bound on their quantum query complexity. So these two methods are very famous. The first one is the polynomial method that I'm going to introduce completely in this lecture. And then by the end of the lecture, I just give you like a few hints of how the adversary method works, and I'll spend the second lecture on the adversary method. All right. So I show you what is a classical query. It's a very natural object. So what is a quantum query now? Of course, here on that picture, this is a classical query, as I previously mentioned. So you have this input, you access it through a black box, you input I, and it returns xi, right? And the complexity is the number of queries to this black box. So in the quantum setting, what you want to do is do these queries on superposition. In fact, this is not the correct thing to do, so because you need to have an oracle, I mean, this black box, I call it also an oracle, you have to make it reversible. This is one way of doing it. This is how what we would consider, I mean, there are other ways of making it reversible, but this is what we will do in this talk. Right, so now my oracle takes two inputs, the index I and some bit b, and it returns I, and the XOR here, this is the XOR mode, or the addition mode 2 of b, and the ith bit of x. All right? All right? And moreover, what you can do is input superpositions. So just to say some symbols, you can also, of course, make a superposition of b, which I haven't represented here. But more importantly, you can query all the bits of x in superposition. It doesn't mean you can learn x with one query, of course, because when you measure, you only learn one bit in the end, but still you have this capability of making queries in superposition. This is the main difference between the classical and quantum query complexity. Okay, so without loss of generality, the kind of circuits that we will consider have the following shape. So we will start every time with the input 0. I mean, the circuit works on the 0 state, and it will alternate. On 0, it will first apply some unitary, and then make a query here, O of x. Right? And then another query, and then O of x again, blah, 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 until in the end we do the last query, last unitary, we end up in some state, and at the very, very end we measure the state. So the state side here, when you measure it, so, okay, there are a number of things to say here. So first, this whole circuit is just one big unitary, right? However, I distinguish the gates. I mean, there are two types of gates here. The unitaries UI, they don't depend on the state, on the input to the problem x here. Right, so it's only these query oracles that depend on the state. So the total number of queries, still, it's given by this t here, the index for the last unitary. And by definition, when you measure the state psi at the end, it is supposed to give you, with high probability, you get the value of the function f of x. Right? This is something important to have in mind. And this q epsilon here denotes the quantum query complexity, which means the smallest such circuit here that I can have for a given function f. And the epsilon in the bottom just means that I'm allowed to err with bounded, I allow bounded errors, which means here that when I measure here, I will not always find the value f of x, I will just find it with high probability. An important feature also, which is also true for classical query complexity, is that if you can prove lower bounds on this, in this model, you can then completely unroll the circuit, and it gives you in turn a lower bound on time complexity. And in fact, for the two functions that I mentioned earlier, element distinctness and the OR function, the query complexity gives you a tight lower bound for the time complexity of this problem, up to maybe logarithmic factors. Okay, so how can you prove a lower bound in this kind of situation? So the recipe for the two methods that I'm going to show is more or less the same. You introduce some quantity here, q, and you want to keep track on how this quantity evolves when the circuit is evaluated, and somehow you want to show that this grows like the number of queries. Right, so let's see how you can do it with the polynomial method, which I think is very intuitive for this. It could show you how you can do that. So the idea of the polynomial method is to try to represent the function that we want to compute as a polynomial. And this idea, it has been proven useful already a long time ago. And it's been used, for example, by Minsky and Papert, who used polynomial representations to represent functions, Boolean functions in the context of AI. By the way, Minsky just passed away last Sunday. He was one of the inventors of some of the things that I'm going to show here. Then, in the context of classical query complexity, already in the early 90s, Nissan and Segediev introduced this idea of representing polynomials, functions by polynomials. And in the quantum setting, the breakthrough paper came out in 1998 by Beals and others. Even more importantly, Mike Moska's PhD thesis contains most of the results that I'm going to show here with lots of details. And one thing that made this method very important for a long time is that with this method, it was possible to prove a lower bound, a tight lower bound for the element distinctness problem. Okay, so the quantity that we're going to keep track here is just the internal state of the algorithm, right? So it starts at 0, it ends up at psi x, and at each step, we're going to look how this state evolves, the internal state of the algorithm. Right, and now if I zoom at like the small teeth round, what I want to really precisely look at is what happens to this state when I make a query. And so before the query, without loss of generality, I have this superposition here. So I is this index that I'm going to query, B is this bit that is supposed to receive the answer, and W here is just some working epsilon. And so the key here, they contain, I mean, it's the superposition. These are the coefficients of the superposition. Right? And the key idea of the method is that these coefficients here, before the T's query, they are polynomials of degree at most t plus 1, t minus 1, sorry. So after the query, it will be a polynomial of degree t, basically. So the degree of this polynomial, it really tells you where you are in the process of evaluating the function. All right, so of course I haven't told you what kind of polynomials, what are the variables here, or anything. This is just a high-level idea. But in details, it's not much of a work to notice that, right? So here I have this query register that will be important, and by definition of a query, what I know is that after the query, the state receives the xi here as proposition. Okay, so now let's focus on just the circle part here with the orange, and I will again unpack everything just to show you there is a very nice way of writing it. So suppose that xi is 0, then you get a 0 in this register if b equals 0, and you get a 1 if b equals 1. So you get this expression. If xi equals 0, you get this expression here. Now, if xi is 1, the situation is reversed, right? So this coefficient, the coefficient that you get here, so if xi equals 0, you get 0 in front of the cubic 0, and if xi is 1, you get 1 in front of the cubic 1, and if xi is 1, then it's the opposite. And there is a very compact way of writing it, which is the following. I mean, it's given by this formula, so if you look at it, if xi is 0, then this parameter is killed, right? So I only get this parameter, and you get 0 in front of 0, and 1 in front of 1. And if xi is 1, then this parameter is killed, and you only get this parameter, and you get you get a 1 here in front of cubic 0, and a 0 in front of cubic 1. So these xi's here are precisely the coefficients of the polynomial that I want to keep track of. And of course, these are only 0, 1 variables, so without loss of generality, you can think of it as a multilinear polynomial. I have lots of different coefficients, but they're all 0. All 0, 1. Right, so now by induction, it's clear that if you think of these coefficients, right, this whole coefficient, it's just a polynomial of, the degree by one query only increases by 1. Right, and so what I showed you here is that if I have an algorithm, quantum algorithm making t queries, then the degree of this polynomial is at most t. So you can write it with the formula here. So the 2. So what I do is after the measurement, so I get a factor 2 because amplitudes eventually become probabilities. And the tilde over the degree is just, it's not a polynomial that computes the function exactly, but that approximates the function. So it's called the approximate degree of the function. It's at most 2t. So if I just now look at if I just reverse the reasoning here, the quantum query complexity is at least the approximate degree of the function. Okay, and an application that I can show you, again, not in full details, but just tell you a bit how it works, is for the OR function. So the thing is that you need to lower bound the approximate degree of multilinear function. So this is not something easy to do. And what we do for the OR function is first there is a first step that consists in making this polynomial univariate by using the technique called symmetrization, and then we prove a lower bound on the degree of this polynomial, which is something much easier to do. So what is symmetrization? So this is exactly what we received, what was shown by Minsky and Papert a long time ago. If you have a polynomial f, then you consider this symmetrized polynomial. So what I mean here is that you will take x, and you will average the value of f over all possible permutations of the bits of x, right? So I sum over all possible permutations of x here the value f, and it's averaged over this. Right? So this is called a symmetrized F. And the theorem that was proven by Minsky and Papert is that when you do that, you can, in fact, represent this as a univariate polynomial, which has the same degree as the original polynomial F here. And the variable of the univariate polynomial is the so-called Hamming weight of x, which is just the number of ones in the bits of x. So just like a two-line proof sketch, how does it work? You introduce this intermediate variables vi here that contain the vi here is just the sum of all degree I monomials. And of course, since if you take one of the monomial and you permute it, so, you get the same. By the action of this permutation here, it's clear that the polynomial f sim here only depends on these variables vi. And then second step. The second step is that these monomials, these variables vi's here, you can very simply express them as these combination factors here. Right, so this is how you build this function g. Okay, and now the second step of the lower bound for f, for the OR function, was given also by a previously known theorem that was proven by Paturi, which proves the following. Okay, suppose you have this function, right? That so here I represented somehow this univariate polynomial. So if the input is 0, the Hamming weight of your if the input has no, it's the all 0 input basically, then the value of the polynomial, it has to be very close to 0, right? Most epsilon away from 0. And now for all other possible values of x, it has to be very high, right? In this stripe here. So the polynomial that you get that way is very steep. By the way, I represented it with the polynomial because it's these are all the basic terms here. And what Paturi has shown is that such a polynomial, it has to be of degree at least square root of n. Right, so this is how you can use the polynomial method to prove a low bound for the OR function, and in turn for the optimality for Grover's algorithm. Right, because then you know that f has degree at least square root of n, which implies that g, this should be a g here. G has degree at least square root of n, so the polynomial that represents, that approximates, any polynomial that approximates the function has degree at least square root of n. And it means that the quantum query complexity of the OR function has query complexity at least square root of n. All right, another very important corollary that you can prove using the polynomial method is that, in fact, query complexity has this very strong property that for total functions, the gap is bounded. So a total function is just a function that is defined on all possible inputs to the problem. And what was known from earlier work is that the classical query complexity is also upper bounded by some polynomial of the approximate degree. This is the degree here. And so I think this factor 6 here is due to Bills and others, but another value is already known. So it means that for total functions, the gap that you can have here is at most a gap of 6. Sorry, between classical query complexity and quantum query complexity. It's at most 6. Right, so, okay, this graph is a little bit silly, but it's just to show you that this story is still active nowadays. So in 1990, between 1995 and 1997, we knew already that for the R function, there was a quadratic gap between the classical query complexity and quantum query complexity, right? So here, it's exactly quadratic. At the same time, not very long after, we knew that the maximum possible gap for any function was at most a factor 6, right? So there was this gap between like the maximum possible gap for any function and the maximum gap that we were able to prove in general. And for many, many years, people conjectured that what should happen is that the blue curve should start decreasing at some point, which means that this factor 6 should decrease. And in fact, it was conjectured that the maximum gap was given by growth, by the OR function. So it was conjectured that the maximum gap was quadratic. And very recently, last year actually, a number of studies came out showing that it's not true. In fact, you can have a larger than quadratic separation given by some function that I'm not going to describe here, but the opposite happened. So the green curve here started increasing. And it was a big surprise. The polynomial method has been applied to a number of other places. So as I already mentioned, it's used to prove a low bound on the element distinctness problem. For a very long time, it was the only tight lower bound that we had. It's been applied to various functions, statistics, threshold functions, read one's formulas, etc. I mean, there's a lot of different applications for explicit functions here. And finally, another very interesting fact is that this technique you can also apply to quantum communication complexity. Sorry, how much time do I have? No? Sorry? 15. Perfect. So before, so that's it for the polynomial method. So before the break, I want to just give you some ideas about the adversary method, because and then I'm going to spend the whole second lecture on the adversary method. So the adversary method, it's a completely different method to prove lower bounds on quantum query complexity. And so basically for the polynomial method, you don't really need to know anything about quantum, right? And the breakthrough of the adversary method was, it started in year 2000, and Minsky proposed this method, the original formulation of the method, where as you will see, it's slightly, it uses some quantum argument, and I think we really needed some quantum intuition to, at this time, to understand the adversary method. Of course, I'm going to smooth it a lot so that to try to make it accessible to everyone, but at this time, it was a big breakthrough. And this, after Minsky proposed his method, a lot of people came out with variations of this method, and the years following in Minsky's paper, you probably would have talked about the adversary methods, because, so I haven't even listed them all. I think there were 7 different variations that were introduced between 2000 and 2004. I'm going to mention some of them in the second lecture, so, for example, you have the weighted version, spectral version, strong weighted, and even a method that is based on Conover of complexity. So completely, it seems completely different from the others. However, in the year 2004, a paper came out by Segedi and Schalek showing that in fact all these methods are equivalent. So none of these, so they all give you the same lower bound on quantum query complexity. You can use, if you can prove a lower bound using one of them, then you can prove the same lower bound with another one. Okay, I believe that at some point, at that point, maybe some people thought the story was finished, but no, because a couple of years later, Hoyer and Schwadek introduced another variation that we called the generalized adversary method. This is this add plus minus here. And they proved that with this method you can beat the original adversary method. You can prove like higher and lower bounds. And in fact, the reason, so the generalized adversary method is really the one you should take home. Right? This is the, today when we talk about the adversary method, we should only talk about the generalized adversary method. And the reason for that is that a couple of years later, Reichardt proved that this method is tight. So it gives you a complete characterization of quantum gray complexity. In the meantime, there was another method also interesting for other things that I'm going to mention at the very end, called the multiplicative adversary method. And the last result in this series, very recently, the generalized adversary method was proven to prove a new lower bound, to reprove the already known lower bound for element distinctness. But for a long time, it was open whether how you can do to prove a lower bound. How you can prove a lower bound using the adversary method for element distinctness, and it was just done very recently by Bellows. All right, so these are the four methods that I'm going to present in the second lecture. Before the end, I'll just give you a very high-level intuition, like the highest possible level argument of the method. And I will spend most of my time on the original adversary method, just because it's simple enough to give you these intuitions. And of course the generalized adversary method, because it has lots of very interesting corollaries. But just to move smoothly from one to the other, I will introduce two of the methods that I mentioned previously, which are the weighted adversary and the spectral adversary. Okay, so just before the coffee break, let me just give you the very high-level argument, and then we'll see in more details how you can do that. So again, as I already said, the goal is to introduce some quantity here that will allow us to keep track of the progress made by the algorithm. Right, so this is this quantity W here, W0 in the beginning, W capital T in the end. And the adversary method, what it tries to capture is the following fact. So at the beginning, this progress function, W, it's independent of the state, right? So what we want to capture in this quantity is the fact that if you look, for example, if you look at the state of the algorithm, then it will be 0 for all possible inputs of the algorithm, right? Because the algorithm starts at 0, we haven't started the algorithm yet, so for all possible input x, the state of the algorithm is 0, right? It's independent of the state. Whereas at the end, I've made all these queries, and if I look at the state, so in particular, if I look at the qubit that contains the value of the function, if my input is such that the value of the function is 0, if it belongs to this set here, then this qubit should be in a state very close to 0, because when I measure it, I have to answer 0. Whereas, if my input is such that it leads to a state whose value, it leads to the value of the function on this state is 1, then I have to be very close to 1. So these two sets of inputs, they lead to almost orthogonal vectors. Right, so this is really what we want to measure. And the way that we do that, again, the intuition is very nice. So this progress function here, you can think of it as having some distance it has to make some progress. So think of the value, the difference between the value of WT and W0 as a distance capital T here. So this is like all the progress you have to make. And on the other hand, if you look at just like one step of the algorithm, which consists in applying this unitary and then computing the query oracle here, calling the query oracle, then you want to prove that the distance, the progress you make is at least, that most is small d, right, by each step of the algorithm. And of course, if you have these two things, then the number of queries you have to make is at least capital D over D. Right. So this is the general idea between the two methods. And in the next lecture, I'm going to show you how it works for the classical adversary, for the original adversary method, I will make all these things more formal, but this is just a very high-level intuition of the method. Okay, maybe I will stop here, and the next lecture I go into the details.